Well, we're ready to begin our study of chemical reactions formally, and this will take sort of quite a while, and we'll come at it from a couple of different angles and see if we can't sort through how all these threads now come together. Remember that chemistry really concerns three big questions: what happens, why it happens, and how it happens. And here we're looking at essentially this overview of what happens when things get together. Matter and the changes it goes through in a chemical reaction, then, chemical equation is a sure, very efficient and powerful way of communicating chemical change. And so that chemical reaction then, in the broadest sense, consists of two different substances. The ingredients or the reactants on the left is what we start with, and then the arrow, and then products on the right, the new substances with different intensive properties on the right, and we simply then use this chemical equation to summarize events. And there's a lot of things that the chemical equation tells us, and there's a few things that the chemical equation doesn't tell us, and we'll talk a little bit more about that perhaps later. But it is a representation of the identities and the relative amounts, and that relative amounts is crucial of the reactants and products, and it's important that you remember that these reactions are taking place on a particle-to-particle basis, so this relative amounts must, of course, be in moles rather than in mass units because of the problem with all those atoms having different masses. Here's just one that I don't even know where it came from, but it doesn't really matter because it just serves as a beginning for us to look at it. Whenever you just see one reaction, one reactant, and then the arrow, what you're looking at is a kind of chemical reaction we call decomposition, and it makes sense. We have a compound that comes apart into simpler substances or decomposes, and here's an example of ammonium dichromate. Dichromate is one of those polyatomic ions. Ammonium, you remember from the previous discussion, dichromate has a charge of -2, and so we have to have two ammoniums that have a charge of +1 in order to have a neutral formula unit. This is an ionic compound. Not only that, but we begin, if we wish to be even more clear as to what is going on, using little symbols to indicate the phase, solid, liquid, gas, or aqueous, of the various reactants and products. More on that later. And so by looking then at this and applying all of our rules that we know about naming compounds and the conventions that we use when we're translating chemical equations into words, we could simply note that ammonium dichromate yields nitrogen gas, chromium-3 oxide, and water. And away we go. Notice that all of these are written with their correct formulas, and the only thing that's new here is that we have put a coefficient in front of the water of 4 so that all of the atoms are accounted for. More on balancing equations, obviously, as we get into this. It's not a huge deal for you because Wolfram balances these things automatically. Most importantly, I guess, is to tie in your senses to chemistry. And here's where we begin to ask the question, what are the indications that a chemical change has taken place? As it turns out, there are essentially 4 big indications of chemical change. The first one is the evolution of heat and or light, and we'll do a number of labs and demonstrations in class where you'll be struck by how amazing it is in some instances where a chemical change will produce a lot of heat and light. Notice that it says evolution of heat and or light. That evolution of heat can also be in the reverse direction, and we'll do a couple of chemical reactions where the system will absorb energy as it goes through a chemical change and draw that energy from the surroundings. And so the container, the beaker, and the surroundings, typically aqueous solutions, will actually get colder as the chemical reaction proceeds. Remember our words, exothermic, endothermic, describing this evolution of heat and or light. Endothermic change means that the system, the reactants are absorbing energy and becoming products, whereas exothermic, the reactants are liberating energy and becoming product. So that's an indication that a chemical change is taking place. Obviously, the energy moving around. Production of a gas is another good indication of a chemical change. Bubbles in aqueous solution or the development of a very distinct odor that wasn't previously detected, both of them are compelling evidence that something's being rearranged at the molecular and atomic level. The formation of a solid precipitate from aqueous solutions, an indication of a chemical change. We'll say a lot more about this when we talk about these kinds of reactions, but if you were to picture, as we will in class in demonstration mode, mixing together two aqueous solutions that are transparent, and all of a sudden the solution turns a milky white or any number of colors, and solid particles can be seen, that's clearly an indication that something is going on in terms of the molecular level. And finally, a dramatic and unexpected color change can sometimes be compelling evidence of chemical changes. The more dramatic and unexpected that color change is, the more dramatic and the more likely it is that you're looking at distinct chemical change. And again, we'll do more of those in class, and you'll see kind of some of these things. So what are then the characteristics of these all-important chemical equations? Oh, you know, I'm really of a mind to just sort of let you sort of go and kind of pick up a lot of this stuff as you work with them, but we'll lay it out for you formally once here. Obviously, the equation must represent known facts. Chemists try, and the things you write down have to be able to occur and have to have been noted. You can't just decide to make up new things on your own. They have to represent things that actually happen. Must contain the correct formulas, and again, we stress all those rules that we used back then to write the correct formulas, and that's a critical thing. And finally, and here's where that whole chemical equation balancing comes into play. In most cases, we have to satisfy the law of the conservation of mass, which means, of course, that nothing disappears, that the atoms of the elements in the reactants and the atoms of the elements in the products must match up. And we do so by adding coefficients in front of reactants and or products as needed in order for everything to work out. But it's important that you not confuse that step with writing the correct reactants and the correct products, because all equations that have the correct reactants and products in them can be balanced. Sometimes we don't bother balancing them because we're looking at the reaction from a different point of view. When we work with these quantitatively, looking at how much reactant we have in lab and how much product we get, we will always have to balance those equations so that we know the ratio of reactant to product. Here's an example of a chemical change that takes place when magnesium metal is put into hydrochloric acid. You've probably seen this already. I think you did it early on in one of the labs. And we make a new compound, magnesium chloride, and hydrogen gas. This reaction is, as you probably remember, exothermic. That is to say, the aqueous solution of hydrochloric acid heats up, and we see the production of a gas. So we have two very compelling reasons to suggest a chemical change. But if we just look at it this way, oh, why MgCl2? Well, there's where your correct formula thing kicks in. Magnesium, as you remember, group 2 is a 2+ ion, and chloride, group 17, is a 1- ion. And so we're going to have 2 chlorides to balance 1 magnesium. So we have to write MgCl2. It is the correct formula. Likewise, note we always write H2 rather than just H, because hydrogen always bonds with itself in all normal kinds of conditions. So looking at this, there's nothing wrong with it. I understand completely what's going on and could talk for probably another 30 minutes about this reaction alone, but The point here is that if you just look at this, it would appear as though we came up with both one chloride and one hydrogen out of nowhere. Notice there's only one over here and one there. And so in order for us then to satisfy this law of conservation of mass, we're going to have to balance it. We do so very simply by putting a 2 right there. And now if you do the count, 1 magnesium here, 1 there, 2 hydrogens here, 2 hydrogens there, 2 chlorides here, 2 chlorides there, and everything is good to go. And in fact, what it means is that if you took 1 atom of magnesium and 2 molecules of hydrogen chloride, you would end up with 1 formula unit of magnesium chloride and 1 molecule of hydrogen gas. More to the point, if you took 1 mole of magnesium and 2 moles of HCl, you would end up with 1 mole of magnesium chloride and 1 mole of hydrogen gas. The coefficients then of the balanced chemical equation indicate relative amounts in moles. Just a few things to tie in here. One is that the arrow is typically pronounced reacts to yield or simply yield. So whenever you see that arrow, you can just insert some language like that. And the phase information again, G, if necessary, stands for gas. L, I know it looks like a 1, but it's an L, is liquid. S is solid. AQ is a very common condition, which means that the substance is in aqueous solution, aqueous meaning a solution of water. You remember that one of the things water is very good at is dissolving things because of its very, very strong dipole moment on the molecule. And although we won't use it for some time, it's worthwhile having in our pocket this idea that many reactions cause the reactants to be quantitatively converted into products, and there is very, very little reactant left. It's also possible for reactants and products to exist sort of in equilibrium. We'll talk more about that. In which case, instead of the single arrow, we have a double arrow pointing in each direction. And this indicates that it's in one of these equilibrium reactions. But again, we won't get into that for quite a while. So that's pretty much all we need. And now we're set to go. And all I'm going to do is sort of walk you through some examples of how you would translate words into equations and equations into words. And then we'll get going on looking at the various major types of reactions.